All right, welcome again. Hello there, Gonzalez here. So, after I look at what the CS, the language C, is all about, and why do we have a C, which is now make it much more convenient to write programs into one specific high-level language that is resemble to English or to something that a human can understand, in this particular case, English. And not only that, but it allows us to write programs that sharpen is our tools. So in other words, so C, writing programs in C allow us to not only define programs or products like payrolls or accounting applications or even web applications, right? But also is developing other programs that takes C as an input, right, and generate now is code that is can be understood by the machine. In other words, binary code. So this kind of programs, so for example, like operating systems, where this allow us to manage the resource, hardware resource, and expose those interface in this realm, the software, so you can now interact with those underlying hardware components, CPU, the memory, the network cards, input and outputs like the mouse or the keyboard or the camera or the audio, right? And also it allows to create now applications that takes C code as source, right? This script or this file written in C, and generate now other or it takes this C code and generate now is the machine code for those specific architecture. So instead of us having to write, for example, is programs per specific architectures, which can be quite tedious, especially in today's where we have now Windows and Linux distros and Unix-based distro like macOS. So luckily for us and for all the people involved in the development of C, like sorry about their name, but I just kind of new to this, Dennis Ritchie and Ken Thompson, right? Well, you get this idea here, right? And the author by Brian Kernighan, which they come up with the first version of the C programming language reference. So what I'm going to do in today's video is by looking at this particular course created by this estimated boot dev and TG devries in terms of how the C programming is and the memory management, because it all starts as one single question, right? It's like how do Ruby or interpreted or interpreted language store objects in memory. So in our case, Ruby, right? Or Python or JavaScript, right? So yes, let's get into this. Here, this is part of the chapter list. We're going to start with the C basics and the struct. The idea is that I'm going to now dedicate roughly 34 minutes to go over this, or to go over 2 chapters per video. So it means that it'll be roughly 6 to 7 or 8, right? Because I also going to look is at the C reference. So not only take what the boot.dev and TG devries author mentioned, right? But it's read at the spec, the source of truth. So yeah, let's get into this. Let's get into this. Mediocrity doesn't cut it anymore. I don't think that is to write a lot of code. It's to understand what that code is, right? So yeah, start the course. It's gonna start here pretty basic with what he start with. That's the whole program. That's the whole point of it. So let me put it here real quick, right? This is the C programming, and that's what I'm going to do here real quick, right? Especially here. Oops. Wait, what? It pulls me all of this. All right. Interesting. Exactly. So, but is this, right? C programming and memory management full course from boot.dev. Okay. So the goal here, right, is to understand how memory is managed by a language. Okay, is to understand how memory is managed by language reading for compilers. Okay, for interpreters, interpreted language like Ruby. Okay. So to understand how memory is managed by language reading for an interpreted language like Ruby, all the way down to all the way down to the CPU. All the way down to CPU for or I will summarize this is to understand, okay, or is to create, is to have a story that describe all the way down on how an object is stored and remove from memory. Yep. To have a story that describe, okay, to have a story that describe all the way down on how an object is stored and removed from memory. Okay, so the specific objective or the this is the goal. You have now the specific objective. Okay, is to well understand that, right? Is to so understand what is Ruby, understand what is this yet another Ruby virtual machine. I think it is yet another exactly, jar, right? Which is the virtual machine, right? Why Ruby use C, for example. What is C? you know, why C? You know, so what is the problem? So what is the problem C is trying to solve? All right. And then, well, how to get myself familiar with the basics of C, right? With the basics in plural, with the basics of C. And then understand how C allocate memory. Okay. Allocate, or you can say store memory. What is allocation? Okay. What are the allocation types? Sorry, store. What is memory? What is memory allocation? What is the memory allocation types? And pretty much is the same to say, hey, what is memory deallocation? Okay. And what are the types of memory deallocation, right? So and here is when things like garbage collector kicks in, right? So you have now garbage collector. So let's get into this, right?
So without any further ado, let's just go ahead and get started. There's a few things that we're targeting to do throughout this course, and this will give you a little preview of what's coming up. The first one is what's going on in memory. How are things stored on the computer? How do things get turned into?
Exactly.
Then we're going to sort of be talking about how to make things more efficient. We're going to get some practice in a proper low-level language like C, and at the very end of the course, we'll be building two different kinds of garbage collectors to give you a firmer grasp of what languages like Go or JavaScript are doing.
That's exactly very much what it's doing. So yeah, understand how a web program store data in memory, which is pretty much all the way down. Learn how and again we are learning is all of this how the mechanism, learn how to make programs more efficient, practice programming in low-level programmings, right? And ultimately is learn about garbage collector and build your own garbage collector, right? So and let's build my own garbage collector, right? To understand what programming language like C, Python, Ruby, or JavaScript are doing behind the scenes, right? The scenes. So without further ado, let's get into this, which is part of the goal of this, right? This is not a C course. We'll be writing C code, and we'll be cover the basic of C that you will need but we're focusing on memory, not C. To answer the question, prerequisite code experience, you should be comfortable writing code in at least one programming language, Python, JavaScript, or Go. It's interesting that they didn't mention Ruby, doesn't matter. And the C basics, right? We expect you to understand basic algorithm, data structures, OOP, and functional programming concept as well. Building sneakland. If you're familiar with super high level language, you are probably used to not think about memory. In this course, we will building the sneakland programming language. Okay, just little part of it. Okay, okay, in C. We'll study about manually managing memory in C, and towards the end of the course, we'll build a simple garbage collector so that sneak land dev doesn't have to think too hard. A small bit of eye note here is that C was originally considered a high level language where it was released, and in fact, in some way, it is. Modern compilers and hardwares are incredibly cool and make impressive optimization. But even so, I think you learn a lot. I think there is a lot we can learn together on our sneak language journey. Assignment. The ultimate crime has been committed. Someone confused Python with sneakland. Ah, okay. Updated the code to print starting the sneakline interpreter. Make sure to keep the new line character at the end of the day. So this is what a basic C language is all about. You have these things called include, right? Which is on a in a comment, right? And here is when I say, all right, let me take a look now at the basic or the notion of the C programming here, right? Especially is the reference. Where is the reference here? Let's go with the 2018, right? If I look at this, it should take me to the programming language course. There you got it. There, bam. All right. Is this real? Programming C. This cover sheets to be replaced by ISO. This was ISO 2018. There you got it. The following document has been applied to this draft. Question: does this mention is all of that, or is just environment, conceptual models, language, libraries? But I don't think. Let me see what is the scope of this. This document specifies the form and establishes the interpretation of program written in C programs, the representation of C programs, the syntax and constraint, the semantics rules, the input data output produced by C programs, the restriction and limitations. But the question: this document does not specify the mechanism of which C programs are transformed for use by data processing system, data processing here, and so on and so forth. So what I'm looking right now is at the any place where I can read about the C as it is, not the history. The development of language C, then is rich. Particularly is perhaps tutorials and courses. C tutorial learn from here. Let me see if this can help me here. This is Dennis Rich at Bell Labs. Holy mother. The development of C language as it is. Okay. C tutorial. That's it. Intro to C. Let me briefly read about this. Okay. C programming here. For system programming language, right? By starting this tutorial, you will join millions of other programmers who have used cprogramming.com to learn C over the past 2 decades. Okay, so look at this introduction and basic C features: pointing array and string, file input and output and command lines arguments, and linked list binary tree recursion as it is. Finish with all of this tutorial. Do some practice problems, okay, and view more tutorial as it is. Okay, so yeah, this is for C tutorials, right? You also have from C++. So C++ is a fork from C, right? Game programming, graphics programming, algorithm, right? Algorithmic efficiency and sorting and searching algorithm. Why this is quite important? Because at the end of the day, if you want to search a needle in a haystack, you want to do that in the most fastest way possible. You don't want to dedicate generations to find that. Okay. So here we are. Okay. Good. Good. C tutorial. Intro to C by A.K.A. All hail to you, sir. This tutorial is designed to be a standalone introduction to C, even if you are new, if you have never programmed before. However, because C++ is a more modern language, if you're not sure if you should learn C or C++, I recommend the C++ tutorial instead, which is also designed for people who have never programmed before. Nevertheless, if you do not desire some of C++ advanced feature, or simply wish to learn C instead of C++, which is what I want to do, then this tutorial is for you. So getting set up, finding a C compiler. The very first things you will need to do before starting out in C is to make sure you have a compiler. I mentioned before, why do I have a compiler? A compiler turns the program that you write into executable that your computer can actually understand and run. If you're taking a course, you probably have one provided tool at your school. If you haven't done so, go ahead and get a compiler setup you'll need in the rest of the tutorial. If you're new on Windows, your best bet is to use code blocks, mean width. If you're on Linux, you can use this compiler. If you're on Mac, you can use the Xcode compiler. That's interesting. So I am on a Mac, right? And if you want to learn downloading Apple Xcode, do I need to do this? Oh, fucking shit. So I can use, if you're on a Mac OS, you can use Xcode for that. Using Apple Xcode, and once you're downloading Xcode, you can install it from the disk, and you can run Xcode from developer application code. Xcode has a lot of documentation and can walk you through setting up a project. The very simple thing to do is to create a new project from file, new project, first application, and then command line tool. This will give you basic command line programs that you can use when you're learning program. Before you leave that screen, make sure to type the project C++ if you're using C++ instead of C. Go through the rest of the prompt and create your new project. Now you have a small project set up and has the main CPP file. You can edit the main CPP, but by default it will include a small sampler hello world. So if I go to now Xcode, right? Xcode. Really? Okay. Oh, you think you are funny? Okay. No problem. Xcode. I don't have Xcode installed? That's BS, bro. What in the French stores? Let me update Xcode. Alright. Okay. 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 It might take a while. Intro to C, right? Okay, so every full C program begins inside of a function called main. A function is simply a collection of commands that do something. The main function is always called when the program first executes. from main we can call other programs, whether they are being written by us or by others, or use built-in language features to access the standard functions that comes with your compiler. You need to include a header with the hash include. Exactly. Directive. What this does is effectively take everything in the header and paste into your program. And let's take a look at our working program, which is this. And let's take a look at the elements of the program. The $include here, right, is a preprocessor directive that tells the compiler to put code from the header, okay, and call studio H into our programs before actually creating the executable. So it's the linking part. And this is telling to the preprocessor here. By including headers files, you can gain access to many different functions. Both the printfl and the get char functions are included in the studio here. So this is a way of how you can tell the preprocessor, okay, hey, before even executing this code, please include whatever you have in this file. And now make that available to that. The next important line is int main. This line tells the compiler that there is a function named main, and that tell the compiler, and that the function returns an integer. Okay. Hence int. The curly brace here signals the beginning and end of functions and other code blocks. If you have programmed in Pascal, you will know then as begin and end. Even if you haven't programmed in Pascal, this is a good way to think about their meaning. The printf function is a standard way to display output on the screen, and I'm assuming that this printf comes from here, right? This is standard input and output. Okay, so this is how you can have access to this functionality. The quote tells the compiler that you want to output the literal string here as is, and the sequence is actually treated as a single character that stands for a new line, right? So we'll talk about this later in more detail. For the time being, just remember that there are few sequences that, when they appear in a string literal, are actually not displayed literal by print, and that n is one of them. The actual effect of n is to move the cursor on your screen to the next line. Notice the semicolon here. It tells the compiler that you are at the end of the command, such as a function call, like this. You will see that the semicolon is used to end many lines of C. The next command is get charge. So again, this is a function that I didn't define that, somebody else defined that, particularly here on this library or this file. Okay. Exactly. So the next command is get charge. This is another function call. It reads in a single character and waits for the user to hit enter before reading the character. This line is included because many compilers environments will open a new console window, run the program, and then close the window before you can see the output. Okay, again, this is what the compiler is doing when you evaluate is this. This command keep the window from closing because the program is not done yet, because it waits you to hit enter, and then it closes that. Including that line give you time to see the program run. That's what I'm laughing because it's here. I'm alive, beware. Finally, at the end of the program, we return a value from main to the operating system by using the return statement. This return value is important as it can be used to tell the operating system whether a program succeeds or not. And again, the OS is this program also reading in C that is taking your program here, and then it's going to create something called a process when you want to run this set of instructions that sits on disk, loading into memory, and call the CPU to evaluate those binary instructions here. So the final brace close of the function, you should try compiling the programs and running it. You can cut and paste the code into a file, save it as C file, and then compile it. If you're using a command line such as Borland C++ 5.5, you should read the compiler instruction for information on how to compile. Otherwise, compiling and running should be as simple as clicking a button with your mouse, perhaps the build or run button. You might start playing around with print functions and get used to writing simple C program and explaining your code. And this is also look at the using variables. All right. Okay. It's close to be downloaded. It's installing. Awesome. Comments are critical for all the most trivial programmers, and this tutorial will often use them to explain sections of code. When you tell a compiler a section of text is a comment, it will ignore it when running the code, allowing you to use any text you want to describe the real code. To create a comment in C, you should round the text with this, right? Okay. When you're learning to program, it is also useful to comment out sections of code in order to see how the output is affected. And then we're looking here at using variables. So far, you should be able to write a simple program to display information type by you, the programmer, and to describe your program with comments. That's great, but what about interacting with your users? Fortunately, it is also possible your program to accept input. But first, before you try to receive an input, you must have a place to store that input. This is where all the notion of storing things kicks in. In programming, input and data are stored in variables. There are several different types of variables. When you tell the compiler, you are declaring a variable. When you tell the compiler, you're declaring a variable. Hey compiler, I'm declaring is a repository. You must include the data type along with the name of variables. Several basic types include char. Several basic types of things that you can store are whether it's char or integer and float. Each type can store different types of data. A variable of type char store a single character. Variables of type int store integer, numbers without decimal place, and a variable type float store numbers with decimal place. Each of these variable types, char, int, and float, is each a keyword that you use when you declare when you declare a variable. Some variables also use more of the computer memory to store their values. So it may seem strange to have multiple variables type when it seems like some variable types are redundant. But using the right variable size, using the same container size, can be important for making your program efficient. So think of these variables as this basket where you want to put stuff, and a good analogy is if you are in the kitchen, okay, you want to have, especially if you are making a pizza, you want to have all of these ingredients ready for you to be, right? You want to have the right amount of flour, they have milk, oil, let's say coconut oil, you're fancy, and your bowl, the thing they use to mix all of that. So you want to have all of these different ingredients in place. because some variables require more memory than others, you know, or space, right? For more, sufficient to say that the different variables types will almost all be used. Before you can use a variable, you must tell the compiler about it by declaring it or telling the compiler about what it is type. To declare a variable, you use the syntax variable types and the name of the variable. That's interesting. Okay. Okay, in TypeScript you do that backwards. The brackets are indicating that you replace the expression with text describing with the brackets. For instance, a basic variable declaration might look like this. Hey, compiler, here is this repository that is an integer. I want to store, and this is the identifier. So note once again to use a semicolon for that, as you can see. Again, but this is just explaining is the basic type of variables that we can have. And then now is reading input. Using variables in C for inputs or output can be a bit of hassle at first, but bear with me, and it makes sense. It will make sense. Be using the scan function. Okay, in this case, the scan functions. Again, all of these are provided by the standard input and output. To read in a value and the printf to read it back out. Let's look at program and then picks apart everything exactly what's going on. You can evenly compile this and run if it helps for you following along for that. But that'll be all for this video. So take care. I'll be right back. Alright, and continue with this exploration about what C language is, right? How to make sense of C in order to answer this question about how do Ruby or any interpreted language store objects in memory, how they allocate memory for that and how deallocate it. So here we are, right? And because what I'm going to do is just to write my first file here, okay, and open now is VS Code to, well, let me open here now VS Code here in a new window tab and show this on top of that and say no, it wouldn't allow me. Good. That's my bending. TypeScript Pro Essentials, no. Not at all. Not at all. Not at all, man. Okay. Okay. Let me create now here real quick is under the test here. And here I'm gonna create is now make there okay. And here I want to open up here. Can you open that for me, my friend? Okay, and there you got it. Take it. And here we are. Alright, so that's exactly what I want to do. Please follow me along here with this, particularly on here. So let me capture now that application. The application here will be now go, and there you go. So what I can do here is now put this on top of that so you can see what I'm about to do. Alright, so I do want to create my first program here. I was gonna call here is hello world. Alright, the CPP right? Here that you got it. Like I do want to open that. Hello, open here, and the tutorial says in order for you to create interactive applications to your users via command line, it is important for you to tell to the compiler what are the libraries that you want to use. So instead of writing your own code, you just reuse them. In our case, reusing is the standard input and output. So this is the way of how you tell in C, well, how you tell the compiler to pre-process these files. In other words, include these files before running your own or compiling your own program. So in my case, I want to say, hey, let's going to include that, right? I also would like to have some additional help here. It says that this is CPP, but I think I shouldn't use this CPP extension. But yeah, that's fine, at least for me. All right. Let me see if I can now use a extension for that in VS Code. So VS Code CPP extension. If you allow me to do that, right? CPP, or C extensions, right? Extensions. Right. In VS Code, there you got it. Exactly. So help me with that as it is, right? C and C++. Let me install that here real quick. Okay, and I can say C. There you go. That's right. Okay, cool. It can also say, hey, you might want to use this CMake here, which is the build tool for you. So it seems that it comes with all of this. It comes from C and C++, C and C++ themes, and the dev tools in VS Code. So far so good, because I do want us to start is from the scratch, right? Which is, hey, I want to make use of this. I want to create this a basic program that interact with the user, in my case, myself. And this program, instead of, as I mentioned before, writing all of the things that might need, for example, how to capture input from the user, how do I pause and wait for that things, and how do I render to the console is the text that I want to. In this particular case, well, I will rely is now on this. Really love about this auto-completion here. This is also powered by the language server protocol, which is a way of how now a IDE can help you to navigate through your code, IntelliSense, go to definitions, right? So, but in this case, I want to pull is from the standard input and output, standard input and output header, right? If you hover click here, you can see now who made this, right? And all of the serious instructions to have access to, right? So all of the different functions that you can use by just importing that in your, again, this is all of the macros here. Again, something we're gonna see that later on. But all of the functions that you can have access to by just importing is this in your program. Okay, cool. Next is They say that you need to create is a function where you define all of its instructions and to notify the compiler that this is the main application or the application that it is the entry point, right? You call then main, right? And main here, right? So main here, the way to define is the body is by using now curly braces. So for those who are from JavaScript and TypeScript programming language that I might be quite familiar with. And the way of how you can now make use of these functions from the library, all right? For example, you say, hey, print f, right? And it say, well, what do you want to print? As a string, you say, hey, I'm alive, right? Say, hey, I'm alive. I'm alive. Beware. And you now pass a specific token that indicate a special character here. So not only that you print this, you use this function to show something to the user, but because programs, once they are, or particularly the compiler, once it generates this code, is going to create now a window, and it's going to evaluate that code, and because there is nothing else to evaluate, it's going to just show you this and close that process. So if you want to now let the program stay alive for some user inputs, right? So you just use get char from that, right? Yeah, get charge here. Yeah, get charge here. It throw me an error because it say, hey, you need a semicolon, my friend, right? Say for this, and then as any function, they must return something because that's how you notify the OS, which is the one who is taking your program that sits on disk right now and loading into memory and call the CPU to create a process that once that process is done, notify the status of your program, and that is usually as a 0 or as 1, right? So now that I have this simple program here, right? Simple program, okay? I do want is to compile this and say, hey, locally, since I already have a compiler that's going to take this code and generate the binary files that is going to be executed, that's going to be used for the OS to be executed. They can say, hey, compiler, please generate the binary executable code from this hello world here. And it say, hey, I expect you to have here. This is one of the reasons here. It say, hey, because this is a compiler is going to run this static analysis, and they say, hey, you lack of this thing, bro. So once you save that, you got it. It say, hey, well, what's going on? You know, did you generate something? And it is, right? So now it generates this thing called a output. You can look, you can read these things, all right? But this is what now is the binary representation of that code. And I might wonder, how do I run this? I just do this. They say, hey, command not found. So, now that I generate is this code, how do I tell the OS to run this binary, right? So if I ask now Claw here real quick, right? So once I generate the binary code from the hello world, all right, .cpp, how can I tell the OS to run the binary? output, right? As a dot out. That's one question. Out for real. Out, right? After compiling, out is just a regular executable file. You run it by telling the shell this. Oh, okay. So I need to be more explicit about that. Got it. Got it. And the other question is, sorry about that. And the other question is that how can I look at the content of the a dot out, right? Raw bytes x dump. Okay, see the actual bytes. Left column is offset, and you got it. So this is one way to actually look at the raw binary output, which is what I want to look at it right now. Really? Okay. I do want to create is a new one, right? Okay, and well, look at this. So here is when you see is this binary representation of my code, right? And holy moly, this is a mind-bending stuff, right? All of the representation of this, right? I don't know how long is this file, but this is it, right? Okay, the binary representation of my code. HBase, the text and stuff, and say strings. You see all of this. So that's interesting. All right, in terms of how you can read about that. Readable string, pull out the text embedded into binary like the hello world message. You can also run as a string out, say strings a dot out. All right, and it's going to pull the strings out of this program. Okay. But what I do want to look is at the internal representations of this, right? You can disassemble, you can file structure, right? File structure, symbols. Since you're in Mac, your out is match O binary, not EL. So prefer O2 or string over dump as it is. So what am I looking at? This. A good first start to look is usually this file. What am I looking at? Okay. So what am I looking at? Right? You're looking now is a binary that is compiling to this architecture. Holy moly. Okay. That's right. Why any readable string? And the other is the actual instructions for that, right? What is the actual instructions here? Holy moly, bro. So you got is this, right? And this is how you can start to see how this register and stuff like that is doing behind the scenes, right? Sub, strand, add, move this register from one. Now add is this a string, you know? Here's where you can start to see is this, right? So store this on address somehow is this particular instruction. Literal pull from malloc here, right? Symbol stop from here, and this one, and this is small program that you can see here that is made of 7 lines in binary instruction or in assembler is 3, 6, 9, 12, 13, and 14 instructions. So that is quite interesting. Very, very, very interesting. And this is exactly kind of want to know what the things is doing. All right. So far so good, because now the next thing is to use variables. And in order to use variables, the most common place to store variables, the most common buckets is integers, chars, and floats. So let's go into now is, well, actually go and create is a little bit more complicated program here. All right. Yeah, a little bit more complicated program here, like this. All right. And that program, so let me actually execute that program, which is, hey, I want to run OS this program. And say I'm alive, beware. It's waiting for that input, and that's it, right? Pretty simple, pretty simple. Everything in console, all right? So far, so good. So once that is done, okay, I want to now is explore how do we store variables here and to create and to look at the most common formats, okay, integer, char, and float. So let's go to now know how to read from input by is, well, get rid of this and follow this particularly mini program to capture that. Right? So the statement star is always in C with the type of bucket that you want to create and the name of that bucket, which is this is a number. Remember, always use a semicolon. I don't intend to store this with anything. What I want to do is to now print to notify the user is, hey, please enter a number. Remember, semicolon. Right? And then I want to wait for the user input, right? Say scan here. And here is interesting because now it's starting to say, hey, whatever token I'm going to receive, this must be is in this particular format. Okay, and this is and then you gotta now assign that. So whatever value that you are using, or whatever value that the input is gonna give you, let me link this and put it into this bucket called this is a number, which store is integers, right? You say this, very well. Oh, it must be an ampersand. That's interesting. It must be an ampersand. You say this is a number. So again, you are telling the compiler, hey, when you see this token followed by a name, this is a way of how you're going to, behind the scenes, is link the data with this identifier. Okay? Remember the semicolon, right? The semicolon here. And after you receive that, you say, hey, let me actually print something else here, right? And say your entering is this. Yeah? You entered this. And I want to show is the value of what you entering here. And this time, because this is not an input, this is not an output. You can just pass is the identifier to this function, to the print function, and then it's going to bind that. So the compiler behind the scenes is able to, when you generate the code, bind that that format of value that you want to print with your reference or wherever you store in that bucket. And after that is wait, get char, right? Wait until you get some user feedback, and then kill this process or say, hey, that'll be all for this process. So once you generate this code, and then so when you write this code, and then you say, all right, so I need the compiler to generate is the binary portable to generate is the binary portable executable code that is going to work across OS and architecture. In my case is the Mac OS in ARM 64 bits, which is the architecture. So yeah, that made me do this. Say, let me compile this code again, right? By default, it generate is an A output, right? So I want to look first at what this output is, and it say, hey, this is now a file that is generated by. This is a binary. This is a program, okay? That is for 64 executed by 64-bit ARM 64, right? So Mac OS 64 for this kind of architecture. And when I want to run that, right? A.out, right? You say, please enter a number. Say, hey, what about 23, right? You enter 23 as it is. Oh, that's interesting. It add that. Yeah, it add that thing. Okay, it's like added that token here. That's interesting. But you get the idea here. So because I made a modification, so I need to recompile this program and executed that, say 23, and there you got it, right? That's interesting. It's not waiting for my. Yeah, it's like it's not waiting. It's not waiting for me to say 23, and now it's not waiting for that, right? So get char here. That's interesting. That's very interesting that it didn't wait for that. Let me again compile the program and run this. Nope, it doesn't wait. Okay. Well. Oh. So what does all this means is that we have seen the hash include and main function before, right? It's just to say, hey, let's going to use this particularly function. So instead of writing our own, the keyword in declare, this is a number to be an integer. This is where things started to get interesting. The scan function works by taking a string and some variable modified with the ampersand here. The string tells scan what variables to look for. Notice that we have a string containing only the percentage dollar here. This tells the scan functions to read an integer. The second argument of scan is the variable sort of, and you will learn sort of and we'll learn more about what's going on later, but the gist is that the scan needs to know where the variable is stored in order to change its value. Using the ampersand in front of the variable tells you get its location and give that to scan instead of the value of the variable. So this is the location of where you're going to store that value. The location. Okay. So when the program runs, each call the scan check its own input to see what kind of input to expect, and then store the value input into the variable. The second print statement also contains the same ampersand D. Both scan and print use. Oh, yep, all right. And in this case, printf takes the first argument after the string, right? The variable this is a number and treat it as though is where the type specified by the format is specified. Okay, so you have now formats to present values here. In this case, print treats this as a number, as an integer, based on the format specified. So what does it mean to treat a number as an integer? If the user attempts to type in a decimal number, it will truncate it. That is, the decimal component of the number will be ignored. So if I try to get smart here and say 23.7, you say, hey, that is going to truncate it. It's going to present is the whole part. The response will vary from input to input, but in no case it is particularly pretty. Of course, no matter what type you use, variables are uninteresting without the ability to modify them. Several options used with variables include the following: multiplication, subtraction, addition. So just want to come with me to see what I'm looking right now. Which is here. I'm reading is this C programming tutorial. Yeah, the multiplies, the divides, the subtracts, the add. It is of course important to realize that modifying the value of a variable inside the program, it is rather important to use the equal sign. In some language, the equal signs compare the value on the left and right value, but in C, double equal is used for that task. Okay. The equal sign is extremely useful. It sets the value of a variable on the left side of the equal sign equal of the value of the right side. Right? The operators that perform mathematical functions should be using the right side and equal sign in order to assign the results to a variable on the left side. So here is a few examples. Here what it's doing, the result of this, note the use of comma and semicolon, and is 24. A equal, the original value of a with 5 added to it. Right? So you modify whatever you have previously and add this 2. So now it is with 29. Right? Does not assign 5 to A. Rather, it checks to see if it equals to 5. Right? The other form of equal is not a way to assign value to a variable. Rather, it checks if the variables are equals. It is extremely useful in many areas of C. For example, you will often use here in such constructions as conditional statements and loop, something that we're quite familiar with. You can probably guess how less than or greater than function. They are greater than or less than. Okay, greater than and less than, right? And there you got it. Okay. Next is part of the if statement, basic if statement. As you can see, nothing too fancy, right? I am quite familiar with that, right? And if you want to write a program from scratch, it's gonna take this, okay? Well, you can actually write that program here, right? To verify our age, I do want to call the compiler here, and then tell the OS to run this program by creating that. So if you follow me along here real quick, right? And since I already have this particular program, most important part of the program, I need a variable, right? Ask for the age, scan for the value, right? And then perform your logic, right? Hey, if you're under 100, you're pretty young, right? If you're under, you're old. If what you introduce is not a number, then you're dead. Okay, you're really old. Suppose, right? Oh, if you are greater than that or older than that, then you have that. So again, I need to compile this program. I need to tell the OS to execute this program and say, hey, I am 29 years old, and say, hey, you're pretty young. And that's it. Okay? Or I can run the program again and say, hey, I now have 100 years old. Say, hey, you're old. If I run the program again, but I say, hey, now I have 130 years, right? You are really old, right? But if I say, for example, these negative numbers, right? You say, hey, you're pretty young. Despite that this might not make sense, but the programs work as expected, all right? So yeah, right? So if I go back here to the if else statements, more interesting conditions of using Booleans operator as it is, right? Then we also take a look at the loops. Oh, it is hosted in Cloudflare. Okay. Loops are used to repeat a block of code. Being able to have your program repeatedly executable code is one of the most basic useful tasks in your programs, whether if you're using now a form, all right? And this is a particular way of how you can, in this case, now print this number, this sequence of numbers, until from 0 to 10 is going to print all of this number as it is. So don't take my word for granted, right? Let's take a look at if that what is work, right? You take a look at it and you say, hey, let's going to initialize this to 0 and execute this block, right? Until the variable is less than 10. So it's going to repeat that, and then after the block is evaluated, it's going to repeat that over and over and over. And in this case, it's going to count from 0 to 9. So again, if I compile the program and then I tell the OS to execute it, so I get this, right? 0 to 9. Pretty interesting. Pretty basic stuff, right? And then from here, you started to create your own agentic Bitcoin distribute social media graph that allows you to participate with different peoples across the world, including Pakistan, Argentina, Venezuela, the US, Canada, India, Southeast Asia, Thailand, Laos. You get the idea. All right. So this program is a very simple example of a for loop, right? You can also have another condition, like for example, while. It is quite dangerous to go with this. Do while and things like that. You can also break and continue. And now, if we go on into the functions in C, right? Unlike Ruby, where you use now def to define a block of code or a function, right? Here, there you go. You should have an idea of their uses and have already used them and define one of these guys of main. Get char is another example of a function, In general, functions are blocks of code that perform a number of predefined commands to accomplish something productive. You can either use the built-in library functions or you can create your own functions. Functions that are programmer right will generally require a prototype, just like a blueprint. The prototype gives basic structural information and it tells the compiler what the function will return, what the function will be called, as well as what arguments the function can be passed. When I say that function returns a value, it means that a function can be used in the same manner as a variable will be. For example, a variable can be set equals to a function that returns a function between zeros and 4, right? So here is when you can now have access to that particular function. After this function execute, which is a standard function that all compilers have, all right, do not think that A will change at random. It will set the value returned when the function is called, but it will not change again. The general format for a prototype is simple: return, type, function name, and the several arguments. So there can be more than one argument passed to a function or not at all, and where the parentheses are empty as it is. If it does not have a return value, functions that do not return value have a return type of void. Let's look at a function prototype as it is. All right. The prototype specifies that the function molt will accept two arguments, both integers, and that will return an integer. Exactly. Do not forget the trailing semicolon. Without it, the compiler will probably think that you are trying to write the actual definition of the function. When the program, and this is interesting to remember that this is a conversation that you always have with this compiler thing, with this program that is expecting the source code and generate is the binary. When the programmer actually defines a function, it will begin with the prototype minus a semicolon. Then there should always be a block surrounded by curly braces, as is in this particular case. Okay, pretty simple, right? So hey, I do want you to multiply is these two stuff as it is. So notice that how print actually takes the value of what appears to be molt functions. So what is really happening is print is accepting the value returned by molt. Okay, not molt itself. The result will be the same if we have used this print instead. All right. So instead of calling now here our function, and this is interesting, here you define is the prototype. You tell the compiler that, hey, this is the prototype of this function that we're going to use if you find yourself down in the code here. And anytime you call it, you already have a reference from that and somehow execute that code for us. However, the code cannot be run without a definition, even though it will compile. Prototypes are declarations of the functions, but they are only necessary to alert the compiler about the existing of a function. This is what we call prototypes, in C, or blueprints, hints to the compiler to say, hey, this is a function that I'm going to define later down in my code, but be aware that that function, if you find that identifier down the road, well, you know what it is. Return is a keyword used to force the functions to return a value. Know that it's possible to have functions that return no value. If a function returns void, the return statement is valid, but only if it does not have an expression. In other words, for a function that returns void, the statement return is legal but usually redundant. It can be used to exit the function before the end of a function. So the most important functional semi-intent question is why do we need function? Function has many uses. For example, a programmer may have a block of code that he has repeated 40 times through the program, And a function to execute the code will save a great deal of space, and will also make the program more readable. Also, having only one copy of the code make it easy to make changes. Would you rather make 40 little changes scattered all throughout the potential live program, or one change to the function body? So will I. Another reason for a function is to break down a complex program into logical parts. For example, take a menu program that runs the complex code when a menu choice is selected. The program will probably best be served by making functions for each or the actual menu choice, and then breaking down the complex tasks into smaller, more manageable tasks, which could be in their own functions in this way. So a program can be designed that makes sense when read and has a structure that is easy to understand quickly. The worst programs usually only have the required function, main, the worst programs, okay, and fill it with pages of jumble code. So then the other is the next switch in case, right? If you want to now branch out your specific code to do a specific stuff, depend of the input, right? So no big deal. And then the thing that might be quite important in the entire thing, especially when you explore things like the pointers, all right? Pointers are extremely powerful programming tools, and they can make something much easier, help improve your program's efficiency, and even allow you to handle unlimited amount of data. For example, using pointer is one way to have a function modify a variable passed to it. It is also possible to use pointer to dynamically allocate memory, which is what we want to know at the end of the day. Okay? If you want to now reserve a space in memory, you can use pointers to dynamically allocate memory here, which means that you can write programs that can handle nearly unlimited amount of data on the fly. So you don't need to know when you write the program how much memory you need. Okay. Wow, that's kind of cool. Actually, it is very cool as well, and also a foot gun. For some, let's just get the basic handles of what pointers and how you use them. So what are pointers? Why you should care? Pointers are aptly named. They point to locations in memory. That's the whole point of this. Think of a row of safety deposit box for various sites at a local bank. Okay, safe deposit boxes at various sites at location bank. Each safety deposit box will have a number associated with it so that you can quickly look up. These numbers are like a memory address of variables. A pointer in the world of safety deposit box will simply be anything that stores the number in another safety deposit box. Perhaps you have a rich uncle who stores valuables, and it's always an uncle, a rich uncle, in his safety deposit box, but decide to put the real location in another, smaller safety deposit box that only store a car with the number of a large box with the real jewelry. The safety deposit box with the car will be stored in the location of another box. It will be equivalent to a pointer. In the computer, pointers are just variables that store memory address. So you have notions of IP address or zip code address, but they are storing is memory address. Pointers are just variables that store memory address, usually the address of other variables. The cool thing is that once you can talk about the address of a variables, you'll then be able to go to that address and retrieve the data stored. If you happens to have a huge piece of data, and you want to pass into a function, it is a lot easier to pass its location to the function than to copy every element of that data. Exactly. So you pass now a reference for. Moreover, if you need more memory for your program, you can request more memory from the system. How do you get back that memory? The system tells you where it is located in memory. That is to say, you get a memory address back. But again, if you require more memory, you're going to talk to the OS for that. Hey, I need more space here. Do you have more? And then the OS is gonna give it to you. And you need pointer to store the memory address. Okay. So that's what pointers is. It's just it's like a variable of memory address. A note about terms. The word pointer can reference either to your memory address itself or to a variable that stores a memory address. Exactly. It can exactly. This is when this getting a little bit meta. Usually, the distinction isn't really that important. If you pass a pointer variable into a function, you are passing the value stored in the pointer, the memory address. Exactly. So when I want to talk about the memory address, I'll refer to it as memory address. When I want a variable that store a memory address, when I want a variable that stores the memory address, I call it pointer. And when a variable stores the address of another variable, I will say that it is pointing to. Okay. Interesting, this distinction here. But at the end of the day, a pointer is a variable that stores memory address. If you're saying pointing to, is that is a variable that is storing is a memory address. The C pointer syntax. You have the variable type and followed by this. Okay, so here you're notifying is that, hey, I want to store is the memory address, okay, to store now an integer, pointing to something, retrieving an address. Okay. I pointed to an integer. P is an integer. So P must be pointed to that integer. So what you're saying here is, hey, I want to reserve space in memory. OS, please, or C, compiler, reserve space in memory for this identifier, okay, as an integer. And when I want to read that data that you store in memory, okay, I want to do this here. Okay, so I want to say, hey, let's want to assign a normal integer. I pointed to an integer. And here you say, read it and assign the address of x to p. In other words, wherever, okay, and assign the address, okay, and assign this location, this deposit box, reference to the p. And then you say, please enter a number. You enter a number. Look at what you did here. You say, put a value in x. We could use it p here, right? And because now p holds a reference, or p is pointing to x because it's holding now this reference of this address, that is the address of x. Okay, so whatever thing that you deposit in x, you can think of this like the deposit box. Okay, this is where now the gem will live, right? So now when you wanna read about that, the content of that. So now the use of pointer to get the value here. Holy moly. Okay. Okay. I'll make a quick pause here. I'll be right back. All right, and continue to look at. Sorry about that. And let me pull this up thing here real quick. Yes. And continue our explorations about is the pointers, right? And why do we have pointers? So what are pointers and what you should care? So pointers, at the end of the day, they are just like variables, but for memory address. And the cool thing about this is that instead of you having to, for example, duplicate data, you just can have is a reference of a memory address, right? Where you can manipulate or mutate the value in that variable that is hosted in memory, right? That's the whole point of pointers here, at least for this huge overview of C language, right? So you have a C pointer. So pointers at the end of the day, they are memory address, right? This is how you can say, hey, compiler, well, this is, I want you to give me is a memory address, all right? And the other is, I want you to now give me is this bucket of this integer, right? One of them is the memory address, and the other is the current bucket for these integers, right? So pointing to something to retrieve an address. So this is how you can actually retrieve the address for them. In order to have a pointer actually point to another variable, it is necessary to have a memory address of that variable also. To get a memory address of a variable, it is location in memory. Put the $ in front of the variable name. Hey, I wanted to, so instead of the value, instead of the content, and this analogy of this deposit box in your local bank is quite interesting and actually very explicit. It say, hey, this deposit box, right? Particularly the pointer is like a locations of where this deposit box is in your local bank. And with the advancements of technology, in that now you can be your own bank by running is your own, for example, Bitcoin node, okay? So what this pointer stuff is doing is giving you now the address, the location in memory of that deposit, right? Box, the deposit box. So it makes a ton of sense. It makes a ton of sense. So whether if you want to look at the memory address on that, or you want the current value of that, but if you want the memory address, you just put this thing here, right? Give me now is the memory address here, and it makes a ton of sense, a lot of sense, you know. So yeah, that's the big deal here. So when you're using now an ampersand on front of the variable name, that tells you, hey, give me is the memory address of that. And in this particular case, you just say, hey, let's going to assign that to our P, right? And now P is not a type of value. It is now is going to store its memory address. Makes a ton of sense. So there is a couple of questions here. Is that if for some reason, if I get this piece of code, right, and then I say, come with me real quick. And then I say, okay, so I have this, right? What I do want is to look at the address here. You know, please enter a number. But before that, I want to print a couple things here, right? Print this and print this, right? I want to print a couple things here, right? I want to print is this is the memory address of x, right? Of variable of integer int x, right? This is the memory address. The question is that how this address are expressed. That's a good question. Is as they are expressed as holy moly, ampersand. Yeah, damn. As they are expressed, no, it's using percentage. As they are expressed as digit, as they are expressed as any other formatting type, right? So this is when now type formatting. Let me actually put it here real quick, a timer, because I don't want to go over too much into this, right? Let me put it here, a timer here. There you go. Cool. Now, yeah, the type formatting in C. Okay. Formatter specified. So my question is that how can I pointer address? There you go. There you go. So you have now a special formatting pointer here, and this is now P. Hey, this type of data is now a pointer here. So let me look is at the address here using an ampersand of this here. Right? Let me look at the address of this memory address of X here. So once I compile this code again, hello world, and then I tell the OS to execute this, right? It say, hey, yeah, let me actually let me use now this break of line here, right? Break of line. There you got it. Yeah, cool. Yeah, that will look much more appealing. Let's go to compile and do this, and there you got it, right? And it's interesting because that is something that is, I didn't assign that. Whoever is assigned that for me is I'm assuming that is at the compiler level, right? Because if I say this, you got this, and if I run that again, I do have is a different memory address, as you can see here. So anytime that I run this program again, so it's gonna generate a new memory address for. So the question is that who give me is this memory address here? All right. So that's interesting. That's a good question. Luckily for us, I can ask Claude to do that, right? Okay. Given the following outputs, right? Who give memory address? Because this is, so my intuition is that is somehow is calling my program that is written in C is somehow is is having a conversation with the OS that is on every program execution. The OS gives this memory address space. The short answer is a collaboration between the OS and the CPU memory management. But the address you are printing, okay, but the address you're printing isn't a real physical address at all. Let me break it down. This is again, I just want to answer the question is that how does Ruby objects, or how do Ruby store objects in the system, in memory, right? And what do we have that's funny direction here? The address you see is virtual, not physical. That, which is made of 1, 3, 6, yeah, 3, 6. What the French is? I don't even know how to count. 3, 6, 9 digits. Okay, is a virtual address. Every process on modern OS, Mac OS, Linux, and Windows gets its own private, imaginary address space. Your program thinks it is own all of the memory, but those addresses are fake, translated to real RAM locations on the fly by the MMU hardware. The memory management unit at the CPU, using page tables that the OS set up. So the chain is the compiler runtimes decides the layout, where the stack, heaps, and globals goes. The OS kernel assigns the virtual memory regions to your process and manage the page tables, and it's all to the hardware. The CPU MMU translates virtual to physical on every axis. Your ampersand x is a stack variable. So you have now a stack, not a heap. So it is address sits in the stack region. The OS handles your process. Why the address changes on every run? You notice that you have this and there's another one, and that's the ASLR, address space layer randomization, a security feature. So in any run, you have now a random address space here. The OS deliberately randomized the base location of the stack and heap, libraries, etc. on each launch so attackers can predict where things live in memory. Oh, now this is a security stuff here. The OS is doing that. Notice the low byte stays the same. While the high bit change, that's the randomized base shifting, but the variables offset within the stack page stay constant. So who gives the memory address? The value of the virtual address, which is the OS allocate regions plus ASL randomize. The layout, stack, heap, and globals are part of the compiler and the OS loader. And then the virtual physical translation is the CPU MMU hardware using the OS managed page table. An actual physical RAM cell, the OS decides lazily when the page is first touched. So yes, the OS is the main actor. And it's interesting that it put main here. But it's not physical memory you're seeing. And the hardware MMU does the actual translation work. If you want, I can show you a tiny experiment to disable SRN to watch the address become stable across run. No need to do that. No need to do that. But again, this is something that is so. So this address, it is virtual. you know. So the question is that why do I have virtual address and not physical one? Physical one. After all, is the physical uh, that matters, right? Provide me source of your findings links, and grill your response. Okay. Oh, it's gonna search about that. Why virtual memory instead of physical memory address operating system benefits? Exactly, it's like so because okay, the OS, the compilers with the OS give me now this virtual memory address. The question is like, why do I have a virtual and not the physical one, bro? The physical is what's matter, isn't it? Welcome to the computer science OS course, bro. Oh, okay. Good challenge. And the isn't physical what matters frame is exactly the right things to poke at. Okay. Let me answer. Then grill my own answer. Why you get virtual address? Wait, what? Chill, bro. Exactly. Mm, wait, what? Okay. Yeah. Um okay. Ready? Okay. Okay. Anyway, so here we are. Why you get virtual address here? Jeez. Anyway, okay. This I don't get. Oh my god. Anyway. Anyway, Jesus. Okay. What you get virtual address. So you as a process never see physical address because the OS plus the CPU deliberately put translation layer between you and the RAM. Okay. So there is a translation layer between the memory, okay, and the RAM. So it's like a gatekeeper, all right? It's like the bouncer at the RAM database. The reason, roughly in order of importance, isolation and protection. Each process gets its own private address space. Process A and process B maps to different physical RAM. A buggy or malicious process literally cannot name another process memory. There is no virtual address it can form that the page table will translate into something else state. So in other words, the OS has this translation table for security. So when you clone a program or when a process is created by the OS, it's gonna give you now is a virtual memory address that it won't collide with other programs. So it makes sense. Every program owns all of the memory is an illusion. The compiler linker can lay out more of a program at predictable virtual address, the stack near the top, etc., without knowing of caring what physical RAM is free at runtime. Without this, every program will need relocation against whatever physical gap exists. Virtual memory hides fragmentations in physical memory, okay, and delegates to the kernel the burden of managing the memory hierarchy. Overcommit using more than that you have. Virtual address space can exceed physical RAM. Call page gets to disk. Okay, call page gets page to disk, and page are allocated lazily. Only maps to physical frames when first touched. Your malloc 1 GB succeeds on a 1 or 8 GB machines, even with other things running on. Sharing and flexibility. Share libraries, copy on write after fork, memory map file, and just all are just points to two page tables, entering on the same physical frame. Trivial with virtual memory, painful without it. Security. The randomized you saw between here only works because addresses are virtual. The OS is free to relocate the stack base each launch here. The kernel here, virtual memory. The virtual memory here. And the memory management units. And this is where you have swap and page faults. But isn't physical what actually matters? Yes. At the moment of access, the CPU must have physical address. RAM chips only understand physical, and your virtual address is split into page numbers plus offsets. The MMU, which is the hardware, translate the page number to a physical frame via page tables. The OS maintain cache in the TLB, and the offset pass through the unchanged. So the accurate statement is physical is what store, virtual is what you name. The translation happens billions of times a second, so you can keep naming things virtually. Reading your own response, the honest answer. Virtual memory isn't free. Every access pays a translation cost. A TLB mistrigger and a multi-level page table walk, 4 to 5 memory access on x68 and 64, and x86 and 64 before your actual access. This is real, measurable performance text. Plenty of systems use physical address directly. Small microcontroller and many embedded RTOS target have no MMU. They run on raw physical address, so virtual memory is a choice the platform makes, not law of computing. macOS, your case, makes it, and Arduino does not. The kernel itself, drivers, and DMA hardware often must deal in physical address. The abstraction is for user process, like your A.O, not universally. And one nuance is on my claim. I say that the offset low bits stay constant last turn, and that's true within the page here as it is. So, but the bottom line is that you get virtual address because isolation. The single address space illusions, overcommitting sharing, and ASLR are worth the translation overheat. For general purpose OS, physical still matters in the sense that it's real storage. One of the things ultimately is that. So we can summarize, okay, right? So we can summarize that the OS, okay, that virtual address is a way for the OS to isolate and protect the memory from other project, from other process. Yeah, it's a way to isolate and protect the memory from other processes. Okay. Mostly yes, but that's the headline benefit, not the whole definition. Virtual addressing is an indirection layer, the OS page table plus CPU MNU, that give each process a private address space, or the illusion of a private address space, isolation protection. It is the most important payoff, but the same mechanism also enables several things you don't get for free from isolation alone. So virtual memory is equal to each process get its own private map of address. The OS and the MMU translate those physical RAM, or translate those to physical RAM on every axis. So that actually makes a ton of sense here. That makes a ton of sense here. Thanks. Thank you. Right? And the memory that deep. Okay. So that's quite revealing. That's quite interesting in terms of understanding why do we have virtual memory, because this is an illusion to have all the available space in memory for your program, where the reality here is that this is a way for the OS, which is the research manager here, to say, hey, if you want to run these programs, I'm going to now assign this virtual memory for you, that it is up to the hardware to translate those addresses on every axis with the CPU to get that and run the instructions here. So that's interesting. So on anytime that you run this program for security reasons, you're gonna have is a different address here, and those address, when you run a process, you're gonna have is your own virtual memory address here to protect from the OS, from OS wise, that process memory from other process. From other process memory here. Makes sense. So you don't mix things here, right? Makes a ton of sense. So if I continue to look at what pointers is and what the thing is all about, so now that makes a ton of sense. So notice that in the above example, the pointer is initialized to point to a specific memory address before it is used. So if this was not the case, it could be pointed to anything. This can lead to an extremely unpleasant consequence to the program. For instance, the operating system will probably prevent you from accessing memory that it knows your program doesn't own. This will cause your program to crash. If I let you use the memory, you could mess with the memory of any running program. For instance, if you have a document opening in Word. Exactly. You could change the text. Fortunately, Windows and other modern operating systems will stop you from accessing that memory and cause your program to crash. Those OS say, no, you're not gonna crash the program, because I'm going to have a virtual memory assigned for this process that is unique and independent for each process. So to avoid crashing your program, you should always initialize pointers before you use them. It is also possible to initialize pointers using free memory. This allows dynamic allocation of memory. It is useful for setting up a structure such as linked lists or data trees where you don't know exactly how much memory will be needed at compile time. Exactly. When you need the dynamically allocation of memory, all right? I don't know. I know that I'm gonna need an X amount of data. I don't know how many data, but it can grow. Okay? It can grow. So if this will grow, well, OS, please give me more memory on demand, right? So you have to get memory during the program's execution. And we'll look at this structure later. But for now, we'll simply examine how to request memory from and return memory to the operating system. The function malloc residing in the standard lib headers file here. Okay. Is used to initialize pointers with memory from free store, a section of memory available to all programs. Mallocs work just like any other function calls, and the argument of malloc is the amount of memory request in bytes. Okay. And mallocs get a blocks of memory of that size and then returns a pointer of the blocks of memory allocated. Since different variables type has different memory requirements, we need to get a size for the amount of memory malloc should return. So we need to know how to get the size of different variable types. This can be done with the keyword size of, which takes an expression standard libraries here and return it as size. For example, the size of integer will return the number of bytes required to store an integer. Okay. And if I want to print this, for example, size of integer, what is the amount of bytes that I need in order to, so this is the memory address. I can say something here and say, hey, what is the size of, but this size of must come from, in this case, from the standard library. Oh, it come from, oh, okay. This is a standard input and output, but now I do need is the standard lib, as it is. So I do need is the standard lib. So I can now read about this size of. In here I say is, hey, what is the size? Okay, size in bytes of an integer, right? Mhm. I think that I can use now D for that to express that. Uh, and if I want to say, hey, I'm gonna clear this real quick, all right? I wanna exit from here. I wanna compile here this process again. It say, hey, that's interesting. Format specify type int must, but the argument has a type unsigned long. So that's interesting because it's telling me that, hey, you should replace this with this specific format here. Okay, long, unsigned long here. There you got it. So now what I have here, the program compiles correctly, and then I want to execute this, and it say, hey, the size in bytes of integer is 4. And 4 bytes, well, it represent is 16 bits. Interesting. 16 bits. Okay. So when you do this kind of stuff here, for example, like this, right? Say integer pointer malloc, right? A value of type void cannot be used here. Cannot be used to initialize the end here. A value of type void cannot be used to initialize an entity of type int. That's interesting. Okay, and this code sets the pointer to point a memory address of the site's int. Okay, to avoid any crash from that, you are telling now to the OS, hey, give me now is spacing memory for this specific types. So hey OS, give me now a special basket or bucket for this thing. So whether it's an integer or a float or a char, makes sense. So it's like you're asking to the compiler, and the compiler tells to the OS, hey, imagine that you're about to make a pizza, right? So you want a bowl for, let's say, 6 people. 6 people pizza, right? So you want a bowl for that specific amount of people, right? And the same for flour and milk and coconut oil if you want to use that, and tomatoes and pineapples. I don't know why would you put pineapples on a pizza, but who am I to judge? And here, when I try to run this, it say, hey, cannot initialize a variable of type int pointer with a value of type pointer here. Okay, yeah, because this what this is giving you is the size of this. Okay. The memory that is pointed. Okay, exactly. Okay. The memory that is pointed to becomes unavailable to other programs. This means that exactly. The memory that is pointed becomes unavailable to other programs. The space in memory that I'm reserving for this became unavailable to other programs. So in other words, I'm using the virtual memory address for that. Holy moly, bro. Oh shit. Note that it's slightly cleaner to write malloc statement by taking the side of a variable pointer to by using pointer directly. So what's going on here? So if I do, for example, is this, right? And instead of saying, yeah, man, I'm starting to see why it is quite hard. Again, it's telling me that, hey, I cannot do that. But again, it's because this is a C++ program. Yeah, it is because it is a C++ program. So if I continue to read here this, right? So this code set PTR to point a memory address of site int. The memory that is pointed to becomes unavailable to other programs. So when you tell now here, you say, hey, this memory address that I'm gonna use to store something, make that unavailable to other programs. This means that the careful coder should free this memory at the end of its usage, lest the memory to be lost to the operating system for the duration of the program. Exactly. This is often called a memory leak because the program is not keep tracking of all of its memory. Know that it is slightly cleaner to write malloc statement by taking the size of the variable pointer to by using the pointer directly here. And what's going on here? Size of with the pointer will evaluate the size of whatever we will get back from dereferencing PTR, which is the integer. Since pointer is a pointer, which is an address space of an integer, the pointer will give us an integer. So side of pointer will return the side of an integer. So why do this? Well, if we later rewrite the declaration of pointer the following, then we will only have to rewrite the first part of this, right? So we don't have to go back and correct the malloc call to use size float. Since PTR will be pointing to a float, PTR will be a float of size PTR. Will still give the right size. This becomes even more useful when you end up allocating memory for a variable far after the pointer you declare, right? And the free functions return memory to the operating system. And that's interesting that this doesn't work. I don't know why it doesn't work. Right? You say, hey, no, I don't work. I want to rename everything here. I say this is a C program. Okay. C programs allow that to do that, but CPP no. Okay. All right. And when I run this, now I can have that. That's a very interesting thing. So I reserve a space in memory by telling, okay. So follow me here real quick, right? So what I did here, right? Yeah, so what I did here is this, right? I change that to not C++, but to C only, and say, hey, um, compiler, please, let's going to assign, so let's going to assign memory, let's going to reserve a space in memory, virtual memory, for of this size, all right? And it's interesting because it's returning is this of this size, which is now the integer, all right? It's going to reserve space in the memory for you. Or, hey compiler, please reserve a space in memory for this type of for this type of value, right? In this case, an integer, and it say, well, I'm going to reserve now a 16 bits to store and represent this. And if for some reason down the line you have to represent more values than that, okay, you can change that too, right? So not only for int, okay, so not only for int, I mean int, all right, but perhaps I want to now represent is more than that, right? It's like 60 or 32, you know, and all of this, right? And that's quite interesting about what are the values that I want to store here in this bucket here, right? And if you want to load down the later on release memory, you just say, all right, it's interesting, I didn't return anything, but I should return, right? Okay, that might explain why this doesn't, anyway. And then if you want to freeze memory, I want to say, hey, please, let's go to free memory from this pointer here. All right. Make that memory address available to other program down the road. Holy moly. So if I go here, right, and then I recompile the language again, yes, right, and then I recompile the language again, and it say, hey, incompatible integer to pointer conversion passing integer to parameter of type voids. So it say that this is not how you deallocate memory. You just only, instead of passing me the pointer, you just pass me is the reference here, not the memory address. You just pass is the value here. If I compile the program again, it say this one, right? And there you go. So this is how you can reserve space in memory by telling the compiler that it's going to ask the OS to reserve a space in memory of this size, right? Hey, OS, I need you to give me is this bucket of this size, right? What I'm gonna put is now integers. Makes a ton of sense. So follow me here real quick, right? After freeing a pointer, it is a good idea to reset it to point to 0. When 0 is assigned to a pointer, this memory address, the pointer becomes a null pointer. In other words, it points to nothing. By doing this, so it points to nothing. So there is no memory address here. When you do something foolish with the pointer, it happens a lot, even with experienced programmer, you find out immediately instead of later, when you have done considerable damage. The concept of null pointer is frequently used as a way to indicate a problem. For instance, malloc returns 0 when it cannot correctly allocate memory. when it cannot correctly allocate memory. You want to be sure to handle this correctly. Sometimes your operating system might actually run out of memory and give you this value. Okay, especially as your application grows and grows and grows and grows, right? So, for example, if you're a bank and you're managing is hundreds and millions and billions of transactions, so that's grow in complexity. And of course, you say, holy moly, the OS doesn't have any physical, it doesn't have any more memory here, right? So I'm full. Taking stocks of pointers. Pointer may feel a very confusing topic at first, but I think anyone can come to appreciate and understand that. If you didn't feel like you absorbed everything about them, just take a few deep breaths and reread the lesson. You shouldn't feel like you are fully grasped every nuance on why you need to use pointer. So you should have an idea, some idea of some of their basic usage. And then you have this next thing called struct. What the fuck? Struct. When programming, it is often convenient to have single name which refers to a group of related values or related behaviors here. Structure provide a way to storing many different values in variables of potentially different types under the same names. So again, struct is a way of how you can define behaviors in programs like C, right? So again, you have the same analogy of the bucket, and in this case, instead of this bucket is being memory address, these buckets now contain several stuff that are useful for you, right? So for example is, hey, I do have now this bucket called math, arithmetic, that only handles is addition, multiplication, subtractions, and division, right? Makes a ton of sense. So this makes it more modular program, which is easy to modify because it designs make things more compact. So structs are generally useful way whenever a lot of data needs to be grouped together. Data and functionality. My question is that does it also work with functionalities, or it only works for data, right? So, it appears that only group data. For instance, they can be used to hold records from a database or to store information about contacts in an address book. In the contact example, a struct will be used that will hold all the information about a single contact name, address, phone number, and so on and so forth. So this is how you can use now struct for storing, to have a bucket of variables. The format for defining structs are like this, where tag is the name of the entire type struct, all right, the struct, the tag name of a single structure, and a member of a variable within the struct. To actually create a single structure, the syntax is like this. To access a variable of the structure, it goes like this, right? So name and the dot notation, so the name of the variable. So in this particular case, hey, this is the struct, right? Example, treating it like a normal variable type, except with the addition of a struct here. Hey, this is struct of this name. Okay. Wait, what? This is struct. Oh, if I do this, holy moly, it lost. Okay. So this is struct of this name, or this bucket of variables will have this identifier. And then I want to have access to here and assign some value to that. And here's an example program here. So this is the database, integer, so I'm going to store his ID, age, and salary, right? And once I want to run this program, I want to assign is this possible values as it is. But in order to assign that, I need to define is the type of a struct or the bucket where all of these variable will have, and with the same of the employee. The struct database declares that it has three variables, age, ID, and you can use database like variable type like int. You can create an employee with a database type as I did above. Then modify it you call with the employee in front of it. You can also return structure from function by defining the return type of a structure type, for instance. So then you have now this struct database function here. I will talk only a little bit about unions as well. And unions are like structures, except that all of the variables share the same memory. Ah, that's interesting. When a union is declared, the compiler allocate, similar with the malloc, right? But malloc, you are asking now the OS to reserve space in memory for these variables in its own context, in its own virtual address here. So when you run your program by creating a process, it won't modify its other spaces in memory or other addresses. When a union is declared to the compiler, allocate enough memory for the largest data type in the union. It is like a giant store chest where you can store one large item or small item, but never the both at the same time. The DO operator is used to access different variables inside a union also here. As a final note, if you wish to have a pointer to a structure, to actually access the information stored inside of the struct that is pointed to, you use now, wait a single moment. As a final note, if you wish to have a pointer to a structure, which is, hey, now I have a reference to this bucket here, to actually access the information stored inside a struct that is pointing to, you use the operator in place of the dot operator. All points about pointers still apply. So hey, the OS, now that I create this data structure where we're gonna this bucket of variables, here I'm going to assign this bucket of variables to using this identifier, and I want to have now a pointer of which is a memory address of this structure here that you store in memory. This is how can I access to the structure variable and assign the value here 12, and if I want to read the memory address of that bucket of variables, okay, yes, you need to the ampersand when dealing with the structure and using pointers to them. And now you have is this, right? So hey, okay, and here you're saying is this. So give me now is the value, all right, that this pointer, in this case, this memory address holds there. What would you think that this might be the value? Oh, okay. Give me the value. Okay, give me the value of whatever this pointer has stored in memory. In other words, it's gonna give you 12. This is a mind-bending bro. Oh my God, what the French toast? So if I copy this and then I paste this here, right? Follow me real quick here. Let me clear the console here and then say, hey, get rid of this. Let me pull this here real quick and say this, right? So the expected value here, it'll be 12, bro. So let me compile this. Let me compile the program. It's gonna generate the binary the binary portable file known as a out. But I want the OS to execute that by saying, hey, run this program, and it say, yes, it's 12. Okay, that is a mind-bending shit, bro. All right. Okay, holy moly. Okay, and then the next one is arrays. All right, so right now I'm here, and the next one is arrays. All right, how you can represent arrays, and then now streams. All right, and then the input and output topic here, which is file input and output here. Hey, I want to read a file, or I want to write a file. You know, F open, right? And you're starting to understand why, for example, SQLite is all about. When you read about the about SQLite, what it say, hey, SQL is not a replacement of Oracle, but a replacement for F open, right? A replacement of F open. Interesting. Holy shit, this is my bending stuff. Okay. Hey, I want to open the file here. Okay. I want to open the files here. And then you have now typecasting here. And then command line arguments. Right? And now things like linked lists. Alright? And then recursion in C, and then variable arg lists, and then binary trees here. That'll be all for this video. All right, take care. Bye bye.